Imagine descending into an abyss where sunlight never reaches, where the pressure equals the weight of a skyscraper on every square inch, and where life persists against all possible odds. This is the dark zone, the bathypelagic realm, a world that begins 1,000 meters below the surface. Its name comes from the Greek word bathos, meaning deep. Spanning down to 4,000 meters, this zone covers vast ocean expanses along continental slopes, seamounts, and mid-ocean ridges. It holds secrets that have remained unchanged for over 8,000 years. Join us on this 10-minute plunge into its incredible origins, its harsh physics, and the bizarre biology that calls it home. The idea of ocean zones traces back to 19th century explorations, like the famous HMS Challenger voyages in the 1870s. These early missions were the first to map the immense depths and reveal that the ocean was not a uniform abyss, but a series of layered ecosystems. The bathypelagic zone begins right where the last hint of sunlight vanishes, typically at 1,000 meters, just below the mesopelagic or twilight zone. The names help us understand the layers. Pelagic means open sea, while bathy signifies deep, distinguishing it from the shallower epipelagic zone, the top 200 meters where photosynthesis thrives. This deep zone aligns with the continental slope, where sediments have built up for eons, and with rocky seamounts that rise from the seafloor. Here, slow currents form plankton trapping eddies, creating small pockets that can boost local life. While its boundaries can vary slightly with light penetration or temperature, the bathypelagic zone consistently plunges us into an eternal midnight across 83% of the ocean's total volume. Now let's talk about the pressure. Hydrostatic pressure builds by 1 atmosphere for every 10 meters you descend. At 1,000 meters, it's 100 times the pressure we feel at the surface. By 4,000 meters, it skyrockets to 400 atmospheres, that's over 5,800 pounds per square inch. This incredible force comes from the sheer weight of the water column above, and it has sculpted life here since the oceans first formed 4 billion years ago. How do creatures survive? They've evolved incredible solutions. Many have incompressible, gel-like bodies. Others have no gas-filled swim bladders, or they have fluids inside their bodies that equalize the pressure. The viperfish even has a flexible skeleton to avoid being crushed. Early explorers, like William Beebe in his bathysphere back in 1934, felt this power firsthand at 900 meters, paving the way for modern titanium submersibles. Without these adaptations, a human body would collapse instantly. Yet, bathypelagic fish thrive, their very proteins adapted to remain stable under the crushing force. The complex topography of seamounts also disrupts water flow, creating eddies that are crucial for survival in this high-pressure forge. Along with pressure comes the cold. The temperature in the bathypelagic zone stabilizes at a near freezing for degrees Celsius, or about 39 degrees Fahrenheit. This chilling stability is a legacy of the Pleistocene ice ages, when cold polar deep waters sank and mixed globally, getting locked in below the thermocline, the sharp transition layer between warm surface water and cold deep water. Salinity is also remarkably consistent, holding steady at 33 to 35 grams per kilogram for millennia. This constant chill and salinity slow down all chemical reactions, including metabolism. The cold is uniform across this vast expanse, from continental margins to mid-ocean ridges, because the currents below 1,000 meters are often incredibly slow, almost stagnant. The origins of this cold are linked to the Earth's cooling crust and ancient patterns of ocean convection. The only exceptions are occasional warm patches around hydrothermal vents, where heat escapes from tectonic spreading zones. For the creatures here, this cold means life in the slow lane. Many fish have extended lifespans, some living for decades, all thanks to their torpid biology. With no sunlight, this world is one of total darkness. But it's not completely without light. Life created its own. Bioluminescence, the ability to produce light, emerged around 540 million years ago during the Cambrian explosion. It was a revolution, with organisms evolving chemical reactions using luciferin to light up the void. An incredible 95% of species in the deep sea glow, using light created by symbiotic bacteria or their own internal enzymes. They flash and glow to hunt for prey, attract mates, or even to camouflage themselves against the faint light from above. The currents are so slow here, nearly stagnant, which amplifies the isolation and makes these light signals even more important. Hydrothermal vents are their own faint glows from chemosynthesis, a process that bypasses the sun entirely and has been active since the mid-ocean ridges formed 180 million years ago. It wasn't until the 1960s, with the advent of submersibles, that humans first witnessed this spectacular light show, completely overturning the old assumption that the deep sea was lifeless. In response to the darkness, eyes here have evolved in strange ways. Some are massive and gaze upwards, while others are tubular, all designed to filter the scarcest photons of bioluminescent light. In a world without sunlight, there are no plants. So, what does everything eat? The primary food source is something called marine snow. This is a constant, gentle shower of particulate organic matter, bits of dead animals, plankton, and waste sinking from the sunlit waters above. It sinks faster when it's ballasted by heavier silica or carbonate shells from dead microorganisms. This material originates in the massive phytoplankton blooms at the surface. Denser clumps of this snow can sink fast enough to evade being eaten in the midwaters, delivering precious nutrients to the depths. Life has adapted to this scarce food supply in remarkable ways. The jawless gulper eel has a stomach that can balloon to 10 times its body size to hold a large, infrequent meal. And every day, the largest migration on Earth takes place. Trillions of fish, krill, and squid journey 1,000 meters up to the surface at night to feast, then return to the deep before dawn. The low oxygen levels here also force creatures to have incredibly efficient gills. In some spots, hydrothermal vents create oases of life, fueled by sulfur-eating bacteria, much like the primordial soups of early Earth. Only about 1 to 2% of the production from the surface ever reaches these depths, but it's enough to fuel these sparse yet resilient food webs. The life here is truly unique. You'll find giant siphonophores, colonial animals that can stretch for kilometers, their stinging cells all working as one. There are hatchetfish, which use mirror-like scales for stealth, their thin bodies slicing sideways through the water. And then there's the anglerfish, where tiny males parasitically fuse to the much larger females, a bizarre solution to finding a mate in the dark. These incredible adaptations arose through millions of years of isolation, turning the immense pressure and total darkness into evolutionary advantages. The ecosystems around hydrothermal vents are based on chemoautotrophs, creating mineral deposits that are now attracting the attention of deep-sea miners. Our exploration of this realm is just beginning. From William Beebe's pioneering dives in 1934 to modern remotely operated vehicles like Huey's Nereus, which was tragically lost in 2014, we've only glimpsed less than 5% of the deep ocean. The tectonic forces that shape this world may still hide the very origins of life. The question of what lies unseen in the other 95% haunts scientists and explorers alike. The dark zone rewrites the rules of survival. It is a harsh, beautiful cradle of extremes. What are your thoughts on this hidden world? Let us know in the comments, and if you want to dive deeper into the mysteries of our planet, make sure to subscribe. Thanks for watching.